Wow, this Avogadro guy was a genius. Way back in the day, 200 and some years ago, he was able to count particles by weighing, or at least say that he thought we could do that. And indeed, it's what we do today. Also, is credited with experimenting with gases quite a bit and realizing that the number of gas particles is directly proportional to the volume if the temperature and pressure are constant. So they didn't have balloons back in the day, but I always said if he had two balloons, one of N2, one of O2, and they were at the same pressure and the same temperature and the same volume, then he knew they would have the same number of particles even without counting them. And yada yada yada. So, yeah, oh yeah, here we go. Two identical balloons. One has zero point 0.21 moles. One has. We don't know how many moles. Yeah, how many moles of oxygen gas are in the? Does the balloon contain? Oh yeah. So, in other words, if we had two balloons at the same pressure and the same temperature, that their volume, 5.6 versus 5.4 liters, would be a relative measure of how many particles we had. So if we knew somehow 0.21 moles of gas in a 5.6 liter balloon, how many moles of gas in a 5.4 liter balloon? In essence, it's just a simple proportion. And so, believe it or not, we can compare different volumes of gas to be a measure of their number of particles without even counting them, without even weighing them. That's a mind-boggling thing. As long as the temperature and pressure are equivalent for both. Because you've studied already, have you or not, the ideal gas equation, PV equals nRT? Anyways, yeah, not even in the same sample, but it doesn't matter if we can pretty much be sure the pressures and the temperatures are the same. We can use those volumes as a measure of the relative number of particles. And you've probably already realized this as well. Also, that these gas laws, gas properties, Boyle's law, Charles's law, Avogadro's law, pretty much a physical thing. We're not really talking the chemistry, the valence electrons, the bonding, the energetics. We're just talking particles running around, colliding into each other, and the walls of the container, and anything else that's in the same volume, creating the pressure we know as air pressure. And Dalton said those pressures act independently, but that's not the topic of this video. So if I had 1, 2, 3, 4, 5, 6 particles of large gas, 6 relative cartoon units of small gas, 6 moles or whatever, 6 billion particles, or here I have 6 of N2, 6 of methane, doesn't matter what the gas is, so the chemistry is irrelevant for the most part. It's just a physical number of particles thing. Doesn't even matter how big they are. I think I've saved this for a different video, so I'm not going to go into it in detail, but Avogadro would also say um, that the volume of a gas, if it's at standard temperature and pressure, totally depends on the number of particles. So if I have more particles, more volume, fewer particles, fewer volume, and it's a linear relationship. Um, yeah, this is a tricky one unless you see a picture. So, you know what? I better balance this equation. Because if it's balanced, the stoichiometry in front of the gaseous species kind of tell me something about the relative volumes that I should use or could use in the reaction. So to balance it, I take two H2 molecules and one O2 molecule to react to give two H2O molecules. If I had this weighing 2 grams and this weighing 2 grams, oh yeah, right, that'll work. 2 grams, 1 gram, 1 gram, 1 gram, 1 gram for a mole. 32 grams, that's 16 and 16. So the total mass over here would be 2 for this one, 2 for this one, 4, 36 grams. And lo and behold, this weighs 18 grams per mole, and that weighs 18 grams per mole, and that would be also 36 grams. Conservation of mass works sometimes. Should. Another way to draw it. Kind of silly, but it works. Balanced equation. So in the balanced equation, I have 2 moles of H2 and 1 mole of O2, or 2 particles of H2 and 1 particle of O2, if you could even see them, which you can't, but the masses all still work out. Well, not only did the masses work out, but check this out. This would be 2 particles of H2, so twice the volume of this one, as long as the temperature and pressure are the same. So 2 liters of this, 1 liter of this make 2 liters of this. This is some higher math, isn't it? Where 2 liters plus 1 liter equals 2 liters. The volumes are not additive like that, but the volumes are, in essence, predicted by the stoichiometry. So here's that same thing again. Or if I had H2 gas plus Cl2 gas gives 2 HCl gas, that's 1 liter of this and 1 liter of this give 2 liters of that. Or anything else proportionally, volumetrically speaking. Or here's my water, H2 gas and O2 gas again. So if I had 2 relative units of volume of this and 1 relative unit of volume of this, that would give 2 relative unit volumes of this, because I have 2 particles and 2 particles, 2 particles here, 2 particles here, 1 particle here per unit. And the masses should all work out as well. Chlorine weighs 35.5, 35.5, 71 altogether. Hydrogen weighs 1 to 1 for a total of 2 grams per mole, or anything less, proportionally. And again, the key is just to balance the equation. So if I balance this equation, wouldn't I put a 2 right here and a 3 right here? And if I did that, wouldn't it be like this cartoon? 1 relative unit of volume of N2, 3 relative units of H2, same pressure, same temperature, give me how many relative units of NH3? Oh, I know the answer already, right? Because I balanced it. This was a 1, this was a 3, this was a 2. So 1 liter plus 3 liters gives 2 liters, huh? Yeah, it's true. The masses are conserved as well. Something to think about. Sometimes confusing, sometimes interesting. And again, doesn't matter what the gas is, helium, nitrogen, ammonia, or methane. If I'm at the same pressure and the same temperature and the same volume, I know I have the same number of moles, even though they would weigh differently, different masses. Oh my goodness, what is up with this? This looks like the law of multiple proportions or something. This is confusing unless I look at a picture. So I'm lazy and I'm in a hurry, so let me look at a picture. So if I had one nitrogen oxide compound being created by 1 liter and 1 liter to make 2 liters, I can pretty much think to myself that it's 1 mole of particles of this, 1 mole of particles of this, and 2 moles of particles of this based on the stoichiometry. Or if I had 2 moles of particles of oxygen to 1 mole of this, that would probably give me 2 moles of particles of this. That didn't come out too well, but I'm not sure how important it is. But the stoichiometry is the key thing, how the stoichiometry can be used to predict the volumes and such. Okay, what about this one? Let's see. Let's say, so here I have 7 relative cartoon units of purple gas. Don't know what it is. And a volume of 1 liter. If I keep my volume fixed at 1 liter, no, as I start to pump in more gas, if the pressure and temperature stay the same, Avogadro would say, well, duh, as you pump in more gas, the volume wants to swell larger. Ooh, I'm not even going to count those. 17. 17 relative cartoon units, so I've added 10 relative cartoon units. If the pressure on top was the same and the temperature was the same, I probably could do I did, an Avogadro's calculation. So 1 liter changes to what liters if I increase the number of particles. Alright, thanks for watching, guys. Have a good one, and I'll see you in class.